So in this video, we'll take a look at the Bohr model of the atom. We'll practice doing some calculations with his energy equation. So you remember that Bohr gave us an equation to find the energy of an electron when it's in any given energy level within an atom. His equation said the energy of the electron when it's in the nth energy level was equal to negative 2.18 times 10 to the minus 18 times z squared over n squared, and this energy would be measured in joules. The letter Z in this formula is the atomic number of the element you're talking about. So Z, the numerator, is the atomic number, which you can find on the periodic table. You remember that his energy equation only works when an atom has one electron. So the most obvious situation where it would work would be for a hydrogen atom. You look on the periodic table, its value for atomic number is a 1. But if you have a helium atom, helium normally has 2 electrons, but you take away one of those electrons, so now you have He positive. Now that it has 1 electron remaining, Bohr's energy equation would still work. Helium is the second element on the periodic table, so its atomic number is 2. Lithium usually has 3 electrons. It's the third element on the periodic table. But if you take away 2 of the 3 electrons, so now it's 2 positive, it's lost 2 electrons, it'll have 1 electron left. And you could now use Bohr's energy equation to describe that 1 electron that's remaining. Lithium is the third element, so Z would be a 3 in that situation. So depending on which element or ion you're using, which problem you're dealing with, Z would be a 1, a 2, a 3, or we could even keep going. The N in his equation is the energy level, or the orbit that you're in. So if you're starting in the first orbit, you'd be calculating E1, and the value for N would be a 1. If you're in the second orbit, the second energy level, N would be a 2, and you'd be calculating E2. So there's Bohr's energy equation. The picture on the left shows us a simple atom with the Bohr model kind of approach. At the middle, that little red dot, that's the nucleus of the atom. And the electron or the electrons in the atom would be in certain energy levels, or sometimes pictured as circular orbits like this. The first orbit, the first energy level, is n equals 1. The second is n equals 2, n equals 3, etc. Now you remember that when we saw this represented in our PowerPoint notes, we noted that the energy levels actually get closer and closer together. You remember that staircase picture. So this picture here, which shows them equally spaced, is a little bit inaccurate. Now, an electron in hydrogen would normally be in the first energy level. So if you picture an electron in energy level 1, that first orbit, that would be considered the ground state for hydrogen. It's called the ground state because the electron is in the lowest possible energy level. But if this atom were to absorb some energy, then that electron that was in level 1, it could take the absorbed energy and it can move to a higher energy level. So perhaps the electron jumps up to level 5. Now that it's in level 5, we refer to this as an excited state. When the electron is in a higher energy level than it should be because it's absorbed energy, the atom is said to be excited. So it's an excited state. Now, let's imagine a situation where the electron in the excited state loses energy. As it loses energy, it falls back to lower energy levels. Now, let's imagine that this electron begins in the 5th energy level, and it falls back to the 2nd energy level. So it's starting in a very excited state, up in level 5, and it's falling back to a less excited state, level 2. Notice if it had fallen all the way back to level 1, then it would be returning to the ground state in this situation. Now, what happens if it falls from a higher level back to a lower level? Well, in that situation, it must lose energy, and the energy that it loses comes out as electromagnetic radiation, and we can detect that. Sometimes we can see it if it's in the visible region. It might show up as a color, or we could detect it in the infrared region or the ultraviolet region of the spectrum, etc. Now, in this particular picture, this is a hydrogen atom with one electron, and it turns out that in hydrogen, when the electron starts off in a higher energy level and falls back to the second energy level, like we've just described, then it releases visible light. So hydrogen, when it falls from a higher level, the electron falls from a higher level to level 2, the energy released will be visible light. So you look at the spectrum that's showing up above. This is the line spectrum for hydrogen in the visible region from 400 nanometers to 750 nanometers. What this picture is showing us is that the red line in that hydrogen line spectrum is the result of the smallest electron transition, the electron falling from level 3 back to level 2. So I'll jump from 3 to 2 would release the red light. An electron falling from level 4 back to level 2 releases the green light. And we actually calculated that in class. We calculated it to be 486 nanometers. The electron starting up in level 5 back to level 2, the one we just described a moment ago, should release that blue line in the spectrum. It should release light with the wavelength that gives us the blue line in the spectrum. Falling from 6 to 2 will give us the purple or the violet line in the spectrum. And that's also shown on the right-hand side. The electron falling from level 3 to level 2 releases red light. Falling from level 4 to level 2 releases more energy, so it releases a shorter wavelength. It releases the green light. From level 5 back to level 2, that's a bigger jump again, so it releases more energy again, an even shorter wavelength that goes to the blue light. Level 6 to level 2, even more energy, the wavelength gets even shorter, so now we're at the violet end of the spectrum with the shorter wavelengths. So what we're going to do here is quickly calculate the actual wavelength of that blue line. So what is the wavelength of light that corresponds to the electron falling from level 5 to level 2? Okay, what wavelength of light would be emitted if the electron falls from level 5 to level 2? So the first thing we'll do is we'll calculate the energy in level 5 and the energy in level 2. The electron begins in level 5, it finishes in level 2. So if you know what you're doing, this would be a good point to pause and plug your numbers into the energy equation and calculate those two energies. So E5 would be negative 2.18 times 10 to the minus 18. We're talking about a hydrogen atom, so Z is a 1, the atomic number, 1 squared. And we're talking about level 5, so N is 5, 5 squared. The energy in level 2 is negative 2.18 times 10 to the minus 18. Again, hydrogen has an atomic number of 1, and we're in level 2, so 2 squared. Grab your scientific calculator or a graphing calculator. Be sure you're using that scientific notation button. Negative 2.18 times 10 to the negative 18, timesing by 1 squared. Go ahead if you like, but for me, that doesn't do anything. To times by 1 squared doesn't change anything. So I'm really just going to divide by 5 squared. So you could divide by 5 squared, or since that's equal to 25, just divide by 25. I get an energy for level 5, negative 8.72 times 10 to the negative 20. This is energy, so its units would be joules. Do the same thing in level 2, negative 2.18 times 10 to the negative 18 times 1 squared, and then divided by 2 squared, or just divide by 4. And that will give me negative 5.45 times 10 to the minus 19 joules. Okay, I hope you're not just watching this, but that you're actually pausing and doing those calculations yourself and making sure you can get the same answers. So there's E5, the energy of an electron in the starting level up in level 5, and then E2, where it's going to end up after falling to the lower level. Step 2, let's calculate the change in energy as we go from level 5 down to level 2. So delta E from level 5 to level 2. When you calculate a change in anything, whether it's chemistry, physics, or math, take the final situation, the final level, and subtract the starting level. Final minus initial is always what the change is given as. So since we're ending up in level 2, E2 is going to be our final level. We started in level 5, so that's our initial level. Take the two numbers we just calculated up above, E2 to begin with, is negative 5.45 times 10 to the minus 19 joules, and subtract E5, which was negative 8.72 times 10 to the minus 20 joules. Okay, pause and grab your calculator. Make sure you can get this answer. Be careful because you're going to subtract a negative number. So don't forget to subtract and then a negative symbol. So negative 5.45 times 10 to the negative 19. I'm using that scientific notation button. Subtract negative 8.72, scientific notation button, and then negative 20. So the change in energy is negative 4.58 times 10 to the negative 19 joules. There's the change in energy as the electron fell from the higher level to the lower level. The reason we're getting a negative value for the change in energy is because energy is lost. So negative sign for delta E, this is only true for delta E, means that energy is lost. Okay, which makes sense. We're going from a higher energy level to a lower level, so some energy is going to be lost. That energy that's lost comes out of the atom as electromagnetic radiation. So we're going to now calculate what wavelength of light is emitted. So step 3, calculate the wavelength emitted. Emitted means released. Since we're losing energy, light is going to be released, emitted. To do this, we use Planck's equation. Planck gave us an equation for energy of electromagnetic radiation that said E was equal to hc divided by lambda. Okay, so we're looking for lambda. We're looking for the wavelength. So let's rearrange Planck's equation. Lambda will equal the h times the c divided by the e. hc divided by e is going to give us lambda. If you're not quite sure how I did that, what I did first in my head was I moved lambda, which was in the denominator, to the other side of my equation by multiplying. So in my head, I'm thinking, I'll do this on the side with a different color. So in my head, I said E times that lambda must equal hc. I just multiplied both sides by lambda, which gets rid of the lambda in the denominator on the right. Now to get the lambda by itself, I need to get rid of the e. So to get rid of the e, it's multiplying lambda. I'll get rid of it by dividing both sides by e. So I'll be left with lambda equals hc divided by e. That's the algebra. If that bothers you, then set up a simple equation like this, which looks like E equals hc over E. Over lambda. We're looking for lambda, which is like looking for the number 3 in our equation. To get the number 3 with these three numbers, we would take 6 and divide by 2. So to get the lambda up above, you would do the same thing. You would take the hc, which is in the position of the 6, and you would divide it by E, which is in the position of the 2. So lambda is hc over E, the same way that 3 is 6 divided by 2, using the same kind of equation. So now that I've got my equation rearranged, let's plug our numbers in. The h is Planck's constant. It's in your notes. It's also in the data booklet. It's a very small number, 6.626 times 10 to the minus 34, and its units are joule seconds. C is our speed of light. It's also in our notes and in the data booklet, 3.00 times 10 to the 8 meters per second. And the E here, the E is the energy that was released. Up above, we said that the energy change was negative 4.58 times 10 to the minus 19 joules, and we noted that the negative sign tells us that energy was released or lost. So what I'm going to do is simply make that a positive number. I'm going to take the absolute value of it and put it down in this equation. So instead of negative 4.58, we'll put positive 4.58 times 10 to the minus 19 joules. Grab your calculator, use the scientific notation button, and see if you can calculate the wavelength. So 6.626 times 10 to the negative 34 multiplied by 3 times 10 to the 8 and divided by 4.58 times 10 to the negative 19. Every time you heard me say times 10 to the power of, I was pushing the scientific notation button on my calculator. So the answer I get is 4.34 times 10 to the negative 7, and because this is a wavelength, we're going to get meters as our units. So there's the wavelength of light that's emitted when the electron falls from level 5 to level 2. Now that wavelength is in meters. Up in our diagram above, the line spectrum had nanometers, so why don't we convert this? We'll take 4.34 times 10 to the minus 7 meters, and we'll convert this. So we'll set up a unit multiplier. Let's get rid of the meters by putting it in the denominator. So meters will divide by meters and cancel out. And let's put nanometers on top, because that's what we're trying to find. We're going to get nanometers as our answer here. So now you look on page 2 of your data booklet, the bottom of that white page, the first white page, and you're told that nano means 10 to the minus 9. So what do I do with that? Well, I say 1 nanometer is 1 times 10 to the minus 9 meters. Now I grab my calculator and I divide these things. So pause and divide them. You should get 434 nanometers as your answer. So there's the wavelength, not in meters, but in nanometers. Let's go back up to the picture here. We were calculating the blue line. The blue line was where we fell from level 5 to level 2. According to the line spectrum up at the top, the blue line is between 400 and 500 nanometers, and it's a little bit closer to 400, so we got 434. That actually makes sense. It makes sense with the spectrum that we see there. The blue line is at 434 nanometers. All right, now before I let you go, in some of your homework problems, or maybe one homework problem, you're going to be asked to calculate a wavelength of light that would move an electron from one level to a higher level. And in fact, you're going to be asked to calculate something like this. To move the electron, let's say in hydrogen, from n equals, well, I'll pick a low number, n equals 3, up to a high number, and we can pick any number we want as a higher number than 3, but I'm going to do something kind of funny. I'm going to say, let's take the electron from level 3, and let's take it completely away from the atom. Okay, let's pull it completely away. So we're not going to move it to level 10. We're not going to move it to level 1,000. We're not going to move it to level 1,000,000. We're going to take it completely away from the atom, which means we're going to move it to n equals infinity. Okay, that little sideways squiggly symbol there, that is the mathematical symbol for infinity. It's like a sideways number 8. Well, how would you do this? How would you calculate the wavelength of light that would let you move the electron not from a higher level to a lower level, but from a lower level to a higher level? And in this case, the higher level is infinity. How would you do this? Well, the answer is the same way we did these. You would start by calculating the energy for level 3 and for level infinity. So step 1 would look the same thing. Find E3 and find E infinity. Now, E infinity is a bit tricky, but we'll come back to that. Once you know those two energy levels, you would do step 2. You'd find the difference in energy. You would take the final level where it ends up, in our case, E infinity, and you would subtract the starting energy level where it began, in our case, E3. Then, once you know the change in energy, you would use Planck's equation to convert that to a wavelength. Now notice, we've been using Planck to find wavelength. Planck also has an equation, E equals h nu, where you could use it to find frequency, right? You could say the frequency is E divided by h. So if you wanted to find frequency instead of wavelength, you would basically use Planck's other equation. So calculating the wavelength of light that would move an electron from level 3 up to level infinity, it really is just the same 3 steps. But there is that one weird thing. How would you calculate E infinity? You know, if you plug this into Bohr's energy equation, you would get E infinity equals, let's just see what we get, negative 2.18 times 10 to the minus 18. This is hydrogen again, so we'll say 1 squared. And then we say over infinity squared. N is infinity. How do I do that? Well, there's no button on the calculator for n equals infinity, so you can't put that on a calculator to solve it. So what you're going to need to do is use some reasoning. When n is going to infinity, what does that mean? It means that n is getting larger and larger. So when n is going to infinity, we're basically just saying n is getting infinitely large. So we're taking negative 2.18 times 10 to the minus 18, and we're dividing it by bigger and bigger and bigger and bigger things. Well, what happens to the answer of a division question when you divide by bigger and bigger things? If you divide by bigger and bigger numbers, doesn't your answer get smaller and smaller? If you divide by 10, you get some answer. If you divide by 100, wouldn't you get a smaller answer? If you divide by 1,000,000, wouldn't you get an even smaller answer? So what happens if you divide by infinity or infinity squared? Well, your answer will get infinitely small. And since it's getting infinitely small, we can say by reasoning, not because of a calculator, that E infinity is going to equal 0 joules. Because you're dividing by something infinitely large, the answer gets infinitely small, which means it's 0. So E infinity, you wouldn't calculate it on a calculator. You'd set it up like we just did here, and you would say it equals 0 joules. Now that you know that E infinity equals 0, you can go ahead and do the rest of the question. You'll know E3, you'll know E infinity, so you can now calculate the change in energy. Then you could take that change in energy and find the wavelength or frequency of light that would move the electron from the third to the infinite energy level. So I hope that helps. You're going to be able to do now some questions for supplementary problems up to the end of the Bohr model. Good luck.